Hey everyone, welcome to This Explainer. As a student of physics, you are about to unlock some of the invisible rules of motion that literally govern everything around us. I mean, from the simple act of tossing a baseball to the majestic, complex dance of the planets in our solar system, there is a hidden logic at play here. Today, our main goal is to completely master the concept of circular motion. We're going to really understand why things spin, orbit, and turn rather than just flying off into the void. Okay, let's dive into this.
So, next time you look up at the night sky, look at the moon. We know it's moving incredibly fast. But here is a profound little mystery to kick things off. If the natural tendency of any moving object is to just keep flying perfectly straight through space, why doesn't the moon just, fly away? Why is it trapped in this endless sweeping circle around the Earth? Questioning our basic assumptions about how objects travel through space is honestly the absolute best way to start understanding the forces that shape our universe. Here is our roadmap for today. We're going to cover forces in straight lines, the circular motion concept, 3 rules of the spin, satellites in Earth orbit, and finally, turning forces and stability.
Okay, let's kick things off with part 1, forces and straight lines.
This all starts with a massive breakthrough in human understanding, perfectly summed up in Isaac Newton's first law of motion. It tells us that an object stays at rest, or continues to move in a straight line at a constant speed unless acted on by a resultant force. Moving in a perfect, endless straight line is literally the default setting of the universe. If you threw a baseball in deep space, it wouldn't magically slow down or curve. It would just keep going forever. It's only because we live here on Earth, totally surrounded by opposing forces, that we don't naturally see this happen.
Think about a hover scooter for a second. When you switch off the engine of a regular car, friction from the road and air drag force it to a stop. But a hover scooter rests on a cushion of air, which drastically reduces that frictional opposition. Because of that, it needs very, very little forward force to keep moving at a constant velocity. It proves a crucial point. Force actually isn't needed to keep a body moving. It's only needed to change its motion. Which leads us directly into part 2, the circular motion concept. So, the real trick here is the direction of the force you apply to a moving object. If you apply a force in the exact same direction an object is already traveling, you just change its speed. It accelerates or decelerates in a straight line. But what if you apply a force exactly perpendicular, at a strict 90-degree angle to the object's path? Something entirely different happens. The object doesn't speed up or slow down. Instead, its path bends. To make an object turn in a continuous circle, you need a force acting continuously towards the center of that circle. We call this a centripetal force, which literally means center-seeking. Now, for the core of the mechanics. Part 3, 3 rules of the spin. Let's qualitatively describe exactly how motion in a circular path works due to this perpendicular force. Imagine you're whirling an apple around on a string. The string pulling inward, that is your centripetal force. There are 3 specific rules you've got to know here. Rule A, if you want the speed to increase, you need an increased inward force, assuming the mass and the radius stay constant. Rule B, if you want the radius to decrease, meaning you pull it into a tighter circle, that also requires an increased force, assuming mass and speed are constant. And Rule C, an increased mass requires an increased force just to keep the speed and radius constant. Swap that apple for a heavy melon, and you have to pull much harder so the string doesn't snap. Whether you're swinging something on a string or driving a car around a sharp corner, these relationships hold true every single time. To summarize it without getting bogged down in complex math, you need a larger force if you increase the speed while keeping mass and radius locked. You need a larger force to decrease the radius for a tighter turn while keeping mass and speed locked. And finally, throwing a heavier mass into the mix always requires an increased force to maintain the exact same speed and radius. Let's look at this on a massive scale. Part 4, satellites in Earth orbit.
We have thousands of satellites orbiting our planet right now. Remember our question about the moon from earlier? Well, for a satellite, or the moon, the Earth's gravitational pull is what provides that exact perpendicular center-seeking force. The satellite naturally wants to fly off in a straight line, but gravity constantly yanks it inward. When the satellite's mass and speed are perfectly balanced with this gravitational force, it falls into a continuous circular orbit. It's essentially constantly falling towards Earth, but it's moving sideways so fast that it just keeps missing the ground. And to put that into perspective, think about the number 24. For a communication satellite to actually be useful, we want it to stay directly above the exact same spot on Earth 24/7. To pull this off, engineers put them in what's called a geostationary orbit, really high up above the equator. Because of those rules of circular motion we just went over, at a specific height of about 36,000 kilometers, the gravitational force dictates that their orbital period is exactly 24 hours. They're traveling at the exact same speed the Earth rotates underneath them, so to us, they appear completely stationary in the sky. Moving on to our final section, Part 5, Turning Forces and Stability. So when a force causes an object to turn around a pivot point, like pushing a door open on its hinges, we call this the turning effect, or the moment of the force. And the rule here is incredibly elegant. The moment is equal to the force multiplied by the perpendicular distance from the pivot. This simply means that how hard you push is just as important as where you push. It's exactly why door handles are placed as far away from the hinge as physically possible. A really small force applied at a large distance creates a massive turning effect, making the door effortless to open. This principle of turning forces is the absolute secret to stability everywhere. Think of a seesaw. It balances in perfect equilibrium because the turning moments of the two different weights perfectly cancel each other out. A lighter child sitting way farther back can balance a much heavier child sitting right up close to the pivot. But now picture a really tall double-decker bus being tested on a slope. An object behaves as if all of its weight is concentrated right at a single point called its center of gravity. If that bus tilts so far that a vertical line dropping down from its center of gravity falls entirely outside of its wheelbase, the bus's own weight creates an unbalanced turning moment, and the whole thing just topples over. So let's wrap up this incredible journey we've been on. Forces are the ultimate dictators of motion in our universe. If you push something straight on, right in its line of motion, it speeds up or slows down. If you pull it continuously sideways, perfectly perpendicular to its motion, it travels in a continuous circle. And if you push it off-center from a pivot point, it turns. All of these vastly different things, from a frictionless hover scooter to a balanced seesaw to a satellite beaming data from space, are really just different expressions of these exact same foundational rules of force. I want to leave you with a final thought to take out into the real world. Next time you are in a car and the driver takes a really sharp turn, pay attention to how your body suddenly wants to lean outward. You know what that is? That is Newton's first law trying desperately to keep you moving in a straight line. So ask yourself, what is actually providing the center-seeking centripetal force that bends your path and keeps the car safely curving around the corner? It's literally just the friction between your tires and the asphalt. That thin layer of friction is the only thing stopping you from flying off straight off the road. Think about the crazy physical forces at play next time you're out for a drive. Thank you so much for joining me for this explainer. I really hope it transformed how you see the physics of the world around you. Keep observing and keep learning.